In this video, I will show you impedance triangle, power triangle, real power, reactive power, apparent power and the power factor of a series RL circuit. See, I have a resistor R which is in series with the inductor whose inductance is L in the circuit, and we are applying a voltage V equal to Vm sin omega t in this circuit. As resistance and inductance are connected in series, let's say the current I is flowing in the circuit. As this is a series circuit, current I will be same throughout the circuit, and in the circuit if I apply KVL in phasor form, I will get applied voltage phasor V will be the sum of resistance voltage drop phasor VR and inductance voltage drop phasor VL. V vector will be the sum of VR vector and VL vector, or VR and VL phasor. Okay, now let me talk about impedance. The word impede means oppose, prevent, or restrain. Impedance in a circuit provides opposition to current flow or prevent current flowing in a circuit, or restrain the amount of current flow in a circuit. Therefore, if you see in a circuit we increase the value of impedance, you will see there will be a sharp decrease in current in that circuit, because increasing the value of impedance means we are increasing the value of total opposition. As a result, there will be less amount of current than the previous condition. Okay, so when the word impedance comes into existence, if a circuit contains inductance L or capacitance C or both, in addition to a resistance, the total opposition offered by them is known as impedance. See, impedance, the total opposition offered to current flow. Impedance will provide opposition to current flow, that means it will decrease the value of current, okay, by an inductor or capacitor or both, in addition to the resistance in a circuit, is called impedance. Okay, this is the original definition of impedance, that if we have inductor, capacitor or both in addition to resistance in a circuit, the total opposition to the current flow in that circuit will be known as impedance. We can also define the impedance by taking the ratio of voltage phasor and current phasor of that circuit. We denote the impedance with capital Z. Now I will show you how do we calculate the impedance of this RL series circuit. We define the impedance as the ratio of phasor voltage V to phasor current I. Impedance Z is the ratio of phasor voltage V and the phasor current I. See, this is the voltage triangle of this RL series circuit. Here we have taken the I as reference, and I is going in the x-axis. Therefore, I can decompose the current phasor in rectangular form like this. I phasor will be equal to I vector plus J0. As it is going in the x-axis or real axis, it will not have any imaginary part. Okay, now see, the voltage VR is also going in the same direction in the real axis. Therefore, VR will have no imaginary part. VR vector will be equal to phasor current I vector into R, no imaginary component. Now look at VL. VL is going in the, see, if we draw the real and imaginary part, you will see our VL is going in the imaginary axis. Therefore, this VL will not have any real part, it will have imaginary part. J I current phasor into XL. Now see, if we apply KVL in the circuit, we get V vector equal to VR vector plus VL vector. So our applied voltage vector V will be equal to sum of VR and VL. Here this VR is given by I vector plus J0, and this VL is given by 0 plus J I phasor XL. See, this I vector is common in both terms, therefore I can take this I phasor common. I phasor R, sorry, here I have to put R, VR equal to IR. Okay, so here I will get R plus J XL. Okay, now see, this is our voltage phasor V and this is our current phasor I. So if I take the ratio of phasor voltage and phasor current, I will get the impedance, and we will denote that impedance with Z, and here Z will be equal to R plus J X L. In a RL series circuit, the impedance Z will be equal to R plus J X L. Okay, now what will be the magnitude of this complex impedance? The magnitude of this complex impedance will be equal to root over R square plus XL square. And what will be the phase angle of this complex impedance? Phase angle will be phi. This will be equal to 10 inverse XL by R. So the magnitude of the impedance of the circuit will be root over R square plus XL square. Now I will show you the impedance triangle of the series RL circuit. At first you have to know what is the impedance triangle. Impedance triangle is a graphical representation of resistance, reactance and the impedance in right triangle. We will indicate the resistance, reactance and the impedance of a circuit graphically by using a right triangle. Then that triangle will be known as impedance triangle of that circuit. Let's say I have this right triangle. A right triangle has three sides. This is the horizontal axis, this is the vertical axis, and this is the hypotenuse of this right triangle. Here you will see we will represent the resistance R in the horizontal axis. The reactance, as this is an inductive circuit, so reactance XL, I will represent that in the vertical axis, and we will indicate the impedance Z in the by the hypotenuse of that right triangle. That representation, that means in this direction we will show the resistance R in the, this is the vertical axis, in this direction I will show you the inductive reactance, as this is hypotenuse, in this direction I will show you impedance Z. Okay, now let me show you how do we draw the impedance triangle of the series RL circuit. See, this is our voltage triangle. In this direction VR equal to IR, in this direction VL equal to IXL, and in this direction V equal to IZ. See, in all the terms this I and this I is common. If we have a resistor, let's say R, if the voltage across that resistor is VR and the current through that resistor is I, you will see if I take the ratio of voltage across that resistor and the current through that resistor, I will get the value of that resistor. Simple Ohm's law. If I have an inductor, whose inductance is L. As a result, it will provide an inductive reactance XL equal to twice phi FL. See, if the voltage across that inductor is VL and if the current through that inductor is I, you will see if I take the ratio of phasor voltage VL and the current I will get the inductive reactance XL. And if in a circuit the applied voltage V and the total current in that circuit is I, if I take the ratio of applied voltage V and the ratio and the total current I will get the impedance of that circuit. Therefore, now see, if I divide the voltage components with the current, I will get the impedance, resistance or reactance. Now see, we have VR equal to IR, VL equal to IXL, V equal to IZ. See, if I divide this V with this I will get the impedance. If I divide this VL with this I will get our XL, and if I divide this VR with this I will get our resistance. So I can say that if we divide each side of voltage triangle with common current I, that will give us our impedance triangle. See, VR by I will give us resistance in this direction. VL by I in this direction will give us XL, and V by I in this direction will give us impedance. See, in the horizontal axis I am representing the resistance R, in the vertical axis I am representing the inductive reactance XL, and in this axis, this is the hypotenuse, we will get the impedance. And this will be a right triangle, and this is the graphical representation of resistance, inductance, resistance, reactance and the impedance. So this will be our impedance diagram of the series RL circuit. Now let me talk about the significance of the impedance triangle. Whenever we will have impedance triangle of any circuit, we can find out total 4 information from that impedance triangle. First one is that we can easily calculate the magnitude of the impedance. See, this is the impedance Z, this is the hypotenuse, this will be the height and this will be the base. Therefore, by using Pythagorean theorem, we can easily calculate hypotenuse square equal to the base square plus height square. So I can easily calculate impedance Z equal to root over R square plus XL square. Number 2, we can easily calculate the power factor. Power factor is the ratio of resistance and impedance. See here, Z equal to root over R square plus XL square. Okay. Number 3, we can easily calculate the phase angle, this phi, phase displacement between the resistance and the impedance, by taking tan phi. Tan phi is the ratio of height and the base. Here height will be XL and the base will be R. We can easily calculate the phase difference between the current, whether the current leads or lags the voltage. See, in this direction we take the reference I, and in this direction we take the voltage V. As a result, you will see in the circuit current I lags V by this angle phi. Now I will show you the power triangle of the series RL circuit. What is power triangle? The graphical relation of real power or active power, reactive power and apparent power can be illustrated using a right triangle, and that right triangle is known as power triangle. See, we can represent the real power P, reactive power Q and the apparent power V, a volt ampere, with a right triangle, and that right triangle will be our power triangle. Let's say I have this right triangle here in which this angle is 90 degree. This will be its hypotenuse, this will be its horizontal axis, this will be its vertical axis. In this right triangle, in the direction of horizontal axis, we will represent the real or active power. In the direction of vertical axis, we will represent the reactive power, and in the direction of hypotenuse, we will represent the apparent. Or power of the circuit. See, this is our voltage triangle of series RL circuit. We can easily draw the power triangle by multiplying each side of this voltage triangle with I. See, in the horizontal axis we have VR. If I multiply this with I will get VR into I, or I square R. So here I will get VR into I, or I square R. In this direction, if I multiply this with I will get IVL, or I square XL. VLI, or I square XL. Now in this direction, if I multiply this with I will get VI, or I square Z. VI, or I square Z. Now see, in the voltage triangle, this is our reference I and this is our V. I will get this voltage V leads I by an angle of phi. Therefore the displacement will be phi, and this will be a right angle. This was a right angle, or 90 degree. So see, I have this VR into I, or I square R. This is known as real or active power. This VLI, as inductor is a reactive component, this is known as reactive power, and this VI is known as apparent power. See, I have drawn a right triangle by using three power components: apparent or true power, reactive power, and this real or active power. So this is our power triangle. Now let me talk about apparent or true power, reactive power, and real power by using this power triangle. See here, this apparent power VI creates an angle phi with the reference axis. Therefore we can divide this VI into two components. First one is that horizontal component. Horizontal part will be in this direction, and that will be the cosine component of VI, because it creates angle with this axis. Okay, and see this axis, the vertical axis is 90 degree with the horizontal part. So I will get in that direction VI sine phi. See, this VI cosine phi will represent the real power, and this VI sin phi will represent the reactive power. Okay, now let me talk about all the power components. At first talk about apparent power or total power. Total power or apparent power is the power supplied by the source in a circuit, and with this apparent power is the multiplication of RMS value of voltage V and RMS value of current I. That's why this is sometimes known as volt ampere. Usually the unit of VA will be volt ampere VA. Now see, the power that is supplied by the source is our apparent power, and we can divide the apparent power into two components: horizontal part, which is real power, and vertical part, which is known as reactive power. Now what is the real power? Real or active power? Real power is the power that is absorbed by the resistor. Here the resistance is R. So I can say that the power that will be absorbed by the resistor R, that will be our real or active power, and we denote real power with capital P, and this will be equal to VI cosine phi. See, VI cosine phi will be real power, or this will be equal to VR into I, or this will be equal to I square R, and this real power will measure the amount of power absorbed by the resistor, and the unit of this real power will be watt or watts. Okay, after that, reactive power. Reactive power is the power stored in the reactive element. We know that when we have an inductor, it stores electrical energy in the form of magnetic energy. I have shown you that in one half cycle it will draw power from the source, and in the next half cycle it returns that power in the source. This is how in a reactive component power moves back and forth from the source and to the source. As a result, you will see there will be no meaningful work is done by the reactive power. And see, reactive power is the VI sin phi. We take the RMS value of voltage V, RMS value of current I, and the sine component of the angle between the voltage and current. Okay, so our reactive power will be equal to Q. This will be the multiplication of voltage into current into sine phi, or you will see in case of series RL circuit it will be VL into I, or I square XL. VL into I or I square XL. You have to remember that this V, I or VL or VR all are the RMS values, and the unit of the reactive power will be VAR, VAR. Okay, now let me talk about power factor. If phi is the angle between the voltage and current, therefore we can write down power factor as the cosine of this phase angle phi. Or if I know the value of impedance, R by Z will be our power factor. Here in case of this RL circuit, impedance is root over R square plus XL square, or we can calculate the power factor by taking the ratio of active power to apparent or total power. Active power is VI cosine phi, and apparent power is VI. Okay, that's it. Thank you.